Thank you very much, Stefan. Thank you, everyone in GTT, for organizing this user meeting. It's always a pleasure to be here in person and present. And also, thank you for all of you in the audience for attending and for your interest. Also, the previous two presentations and some of the presentations that we listened to during the week, they are very interesting, and I think they provide the context for progressing in that scale that Moritz showed before, from microscale, mesoscale. We listened this morning to a couple of presentations in the process scale, and I guess the next step up, above the screen, it didn't fit in the screen, I guess, is a plant-wide simulation, which is mentioned here. So I'm gonna, my presentation, and I guess that's where SysCAD comes in, takes all of these very interesting tools into that dimension, if you want. And also, I'm gonna focus a little bit on the development of this interface, which has already been released for 7 years. So these are a little bit of the overview of my presentation. So I'm gonna, for those of you who haven't seen SysCAD, a very brief introduction of what SysCAD is, a review of the process of the ChemApp for SysCAD interface, and of course benefits and advantages of using SysCAD with ChemApp, and also from the ChemApp point of view, what would be the advantage of integrating it into SysCAD. Some of the challenges and learnings of this whole process through the development, working with clients, and so on, and what is next steps. So I'm not going to spend too much time in the description of SysCAD. You're going to see some examples in my next slides, but in very few words, it's a very powerful and flexible plant-wide flowsheet simulation with steady state and dynamic solver modes. You can simulate from very simple processes all the way to a very large and complex plant simulation. And it provides a number of tools that I guess is a little bit of the objective of my talk, to facilitate the use of SysCAD or ChemApp, and take advantage of all of those enterprise level tools that will ultimately help users gain insight in their process design, development, updates, and so on. A little bit more narrow in context. Now, within SysCAD, we have something that we call a TCE interface, that stands for Thermodynamic Calculation Engines. And you will see in this list here that we have ChemApp as one of the different TCEs that you can integrate into SysCAD, but that's not, of course, the only one. There's OLI, AQSol, FreakC. All of these different interfaces are developed by other third-party sort of companies. Their own products on their own, but you can bring this into SysCAD as well. And more importantly, you can combine some of these in the same flow sheet. So you might have an aspect of your process plant that requires hydrometallurgy or aqueous chemistry. Then you can pick one of those, OLI, AQSol, or FreakC, which are specialized in aqueous chemistry. And then on the high temperature part, you can have ChemApp, and they all communicate each other. There's seamless integration between all of them. Another thing that is important to mention, since the beginning, since the first release of SysCAD for ChemApp for SysCAD, sorry, it supports constraint-free energy. Things Moritz is very happy with that. But yeah, that's a method that is implemented there because of from the beginning we realized it's important to take into account that in real life the processes not always have the chance to reach perfect thermodynamic equilibrium. So it's important to have the ability to activate those constraints that might represent mass transfer or kinetic limitations and so on. So how it works? I'm going to show more examples about the different unit models that we have for thermodynamic calculation engines, in particular with ChemApp. But in general, and as I mentioned, ChemApp is part of the family of different TCEs. And therefore, it's important to have some kind of mechanism that allows all of these TCEs, even ChemApp as its own, able to communicate with SysCAD native streams definition, right? Like we use our own SysCAD database, own species definition, and sometimes the database that we use in one process model might be larger than what is included in the CST file that we need for ChemApp. So there is a need for translating that information before we call the equilibrium calculation. And similarly, once the equilibrium calculation is done, then there has to be a mechanism to map that back to what SysCAD understands, and then that information can be transferred downstream or to other applications. So this is what is a little bit represented in this diagram here. Everything in blue represents a SysCAD stream. Okay, so imagine there is a number of streams that are coming into a reactor. So there is a forward mapping that needs to occur before it's provided to the thermodynamic calculation engine, in this case, ChemApp. And then ChemApp calculates, generates some results, and then we need to translate that back again through a reverse mapping system to a SysCAD product. And this is really important, and I think is one of the key concepts of the ability to incorporate all of these different ecosystems, if you want, of different thermodynamic calculation engines, especially in the aqueous chemistry where you have solutions with ions, and then you need to recombine the ions to maybe, if you don't want to express that into your SysCAD database and so on. So there is a very automated mapping algorithm that allows you to simply connect one unit to another, ChemApp fitting into OLI or FRIXI or SysCAD units and so on. And automatically this happens without you even needing to realize that it's happening under the hood. But that's done automatically with SysCAD, and it's a very important concept of how this whole thing can work together. A little bit of the history of the development of this interface. So the first release was in 2019. And at the time we did had the opportunity to present, to present here at the GTT users meeting. Also, I think presented at the FAXH workshop at that time that was also in person. So, and we discussed the first example for nickel laterite smelter. Then we progressed, adding more features, incorporating dynamic simulation or specialized units for dynamic simulation, which we present later also in one of these GTT users meetings for a dynamic copper converter. I'm going to show a little bit of that later during the presentation. In 2023, we presented an example using the Tereda database, which I don't know if you're familiar with. That's also developed by another group, but it's specialized in aqueous chemistry with ChemApp. And even though, and we demonstrate that for potash processing using that database, what is important to mention there is that the Tereda database is a reference sort of, it doesn't provide enthalpy information. You cannot really use it to calculate a heat balance. But SysCAD, during this whole mapping in and out frame, can take care of that part. Like, so you can have a purely phase stability thermodynamic calculation for that purpose, but then SysCAD around that will do the heat balance based on its own database. So it can mix and match the two things. And that is, for example, the case in FRIXI. Also, is a database that doesn't include any enthalpy data. So it's very flexible in how you can incorporate all of these specialized databases and so on. Continuing that, we have done, of course, many improvements, incremental improvements in terms of reporting tools, functionality, and for the next release of SysCAD, we will support the 64-bit version of ChemApp, the cloud version of ChemApp, and of course, we are working continuously to extend the database of unit models for specific pyro models. All right, so let's move on to why use ChemApp for SysCAD, and how we, from SysCAD, also benefit of incorporating ChemApp into our platform. So one thing that I mentioned is that you can take this to the next level of abstraction. So this is an example of a full plant for integrated primary copper production, including crushing and grinding of a copper ore. flotation circuit, all of these including particle size, full particle size distribution for different purposes on the grinding and crushing, in terms of separating, predicting the breakage of rocks and into smaller particles, and then adding kinetic information for the flotation circuit, and then continuing with a smelter plant. So you see here 3 different graphic views. This is the same model. It's basically one single model. All of the pages are connected among them. And in this particular case, the smelter includes a number of ChemApp reactors. So there is a furnace, a number of slag blows, or Pearson-Smith converter steps, and also anode refining, desulfurization, and deoxidation step before casting. All of these that you see here, sorry, it's hard to point with this. Anyways, all of these in the high temperature side of the flow sheet, the furnace, the converters, the anode furnace, they're all ChemApp reactors. They look like any other SysCAD unit model, and basically the only way that you can distinguish that they are something different is when you go into their sort of configuration, and then you see, oh, this is a ChemApp reactor. You can set up hydrothermal calculation, enthalpy target calculation, and so on and so forth. But as you can see, they are fully connected with a large process plant model. This is an example we recently published. The idea here, and we have listened about optimization in some of the previous presentations. The idea was here to compare in a plant what happened if I take only the mineral processing side of the plant and try to optimize that, basically just looking at KPIs from the mineral processing side, and then doing the same with the smelter side, try to optimize what would be the operating conditions to recover the maximum amount of copper and so on, as Shivani explained, on the smelter, and then look at an integrated view and optimize the whole plant in entirety, and find whether that gives it even a better optimum in terms of process. And so that analysis, if you want, I can share with you the reference. It's very interesting. But we do this with optimization tools, the same that we've seen with Python and so on. Another thing that, to mention just very quickly in this, it's almost small to see here, but each one of those little boxes there represent a different CST file. So in SysCAD, you have the ability not necessarily to import one single CST file. You can have many of these CST files. It could be different species solution or different databases, because sometimes you might want to have a different system altogether in one part of your process as opposed to what you would use, for example, for the furnace. Sometimes you have a copper smelter next to a lead smelter or something. You may want to use different CST files so that you have full autonomy on how many of these CST files you can load into the model. One thing that you gain when you bring in SysCAD, sort of ChemApp into SysCAD, is a number of tools for control. The first one that I'm going to show here as an example is feed-forward control. This is a subset of the nickel laterite smelter example. Okay, so there's the rest of the flow sheet here that is not shown. But basically, this represents the electric furnace part. And what I wanted to show you, one unit model that we have in SysCAD is what we call a site calculation. This is a full ChemApp reactor. But basically, you can think of this as, I want to take a sample of the calcine, for example, that comes from a kiln, by the way, a unit model, and that also use ChemApp, and analyze that in a site calculation and perform a phase target calculation to calculate what is the liquidus temperature of that particular mix. So I can change the feed ratio or operating conditions upstream, and that will automatically be fed into this site calculation. It's like somebody take this to the lab and say, hey, give me the liquidus temperature. I can then use that information, like this is calculated every iteration, put that into a feed-forward controller here. And so this is the value that I'm monitoring. And based on that, I'm going to set the electric furnace temperature to 100 degrees above, for example, that liquidus temperature. So I always ensure that the furnace is operating at a given superheat. And then I can use that to calculate or optimize what is the blend of feeds that will allow me to operate at no more than 1650 degrees, for example, in the furnace. Okay, so very, very powerful too. So those are all integrated into the model. You just drag and drop them, and off you go. Another type of controller is sort of like a iterative controller, a feedback controller, where in this particular case, in the furnace, we wanted to control the amount of oxygen that will result in a given copper grade in the mat. Okay, so that's some similar example that Shivani showed before, but now you can do that with basically this PID controller. And by the way, in SysCAD you have all of these sort of monitoring tools. You can just create a new trend and say, I want to monitor this and that variable. And actually here you can see the evolution of the amount copper in the metal, in the mat, compared to a set point as a function of changing the amount of oxygen that goes into the converter. So that optimization happens automatically within the graphic user interface. And then there is what we call a general controller. So you can build a very complete and complex process flow for the entire plant without having to program any single line of code. But of course, there's always something else that you might need to do. And for that, SysCAD has its own programming language, which is called PGM. Okay? It looks something like this. This is sort of like the VS Code extension for PGM with highlighting and everything. And the advantage of that is that you can communicate directly programmatically with any ChemApp unit model. So you can ask, okay, perform the calculation now, you can trigger calculations, you can ask for results, you can set inputs, all of that programmatically. And also you can create a sort of like a custom view of the process that you want, like you create this layout. All right, so moving on to another feature that is important and is sort of very automated in SysCAD is the fact of unlimited recycling streams and automatic parallelization. So when we have a process example like this one, so we have a furnace, converters, copper blow. If you examine this diagram, you will notice that some of the slag that is being produced in the converters is actually being recycled back to the furnace. So that creates automatically an iterative condition for the solver. But also, in this particular example, and this is important from a practical point of view, by the way, because this will maximize the recovery of copper while minimizing the oxygen consumption and so on. And then also, there is the recirculation of the copper residue from the last copper blow, mash or slag, whatever you want to call it, back to the first slag blow. Remember that this is a sequential process. We are abstracting this in a steady state model. Therefore, when you finish the copper blow, that converter actually becomes available for the next slag blow. So that residue needs to be recycled if you were looking at this from a steady state point of view. Okay? What that means, when you want to solve this, and by the way, you just draw the lines here, connect one unit to another, SysCAD automatically detects that means this is a recirculation. You don't need to tell that, hey, I have a couple of recirculations, take care of them. And what it does is you hit run, you want to solve this, and SysCAD does a sort of like a flow network analysis, and this is a representation of that analysis. Basically, it's equivalent to the figure that we just showed before. On the left-hand side, you see all of the feed that user settings, right? You say how much feed of this and that and conditions and so on. And this start being evaluated. Each one of these little boxes or circles represent one unit model, and the lines represent the connection between them. Okay? Then when you have recirculation, then SysCAD automatically detects what are it uses like a TER solver sort of algorithm, and detects, okay, I need to bring the output of the, sorry, wrong one. I need to bring the output of the converters back inside to the feed, and SysCAD needs to iterate and solve this until these two values are exactly the same, right? And you need to basically tell that's done automatically. And then the other thing that you can look at here I have highlighted there all of the different 4 ChemApp reactors that are in this model. So the third Pearson-Smith converter is there, the furnace, and then the 2 converters that represent the slag globe. If you look at this, you see that there are some parallel branches that need to be solved and before you can move on to the next evaluation. Normally you would do this, okay, yeah, take one branch, solve that, and then go back, take the other branch, and like you would need to manage that somehow. Well, in SysCAD that happens automatically. SysCAD automatically breaks this down into different threads, and even actually spin off different ChemApp instances for each one of these, so they get solved in parallel. And this is the result of that particular simulation, starting from a fully initial series state of the model. In one of these trends, you can see the evolution of the different results. I'm not going to go into details of which one of exactly what those lines mean, but what is important maybe here to notice is, and apologize for this, I moved the figure the other day without realizing this arrow should be pointing here to this line. This is the number of counts that are being made to ChemApp as this process is being solved. Automatically, there are like 70-something calls to ChemApp just to solve this in a total of 18 SysCAD iterations. So you see, even though there are 18 global iterations, these are solved in parallel, so we need to call ChemApp multiple times. This is an example of a dynamic copper converter. Again, taking this a little bit one more step further, you take the steady state conditions, but then also we have specialized unit models for dynamic modeling, and you can see here a time evolution of the batch processing for a copper converter. I'm gonna move ahead. Another aspect that we have listened already during the conference is this ability for doing automation with Python. There is also a Python SysCAD interface. So imagine it's like ChemApp for Python, but in storage. You can control fully from Python a optimization of a process here. So all of that you see there, each one of these is Python taking a decision of changing input variables to try to optimize a number of different variables. So just to finalize, some of the key features of integrating ChemApp into SysCAD, it allows us to bring up true heat balance. That's something that SysCAD is not sort of capable to do because it doesn't have solution thermodynamic in its database. But when we bring in ChemApp into SysCAD, we can then say, okay, I want the heat balance to be done with full excess parameters and so on. Constraint-free energy, that I mentioned that before. And also bringing ChemApp into SysCAD truly transform the concept of localized point thermodynamic calculations and being able to bring this all into the plant-wide process simulation. There's another advantage, of course, of bringing in to SysCAD, like the full graphic user interface, the steady state and dynamic models, and so on. Excel integration, and a very robust API support for machine learning that can, of course, be used to control SysCAD. Some of the challenges, very quickly, we have, of course, been able to successfully implement ChemApp in SysCAD, but that hasn't been without any challenges. However, it's important, I guess, leave that with you. You can review that later. It's a very powerful tool. We're really happy of the state of the interface right now. We have heard, what do you need to run something like this? Of course, you need a CST file. And we've heard for FACSIT users, it's very straightforward. You have FACSIT, generate your CST file, and then you import that into SysCAD automatically. But this figure a little bit also shows the map of what other sources you can or alternatives you have to generate those CST files. What's next? Continue strengthening the technology in partnership between SysCAD and GTT, expand the library of ChemApp unit models, and improve strategies for solve large systems, speed up the calculations. That's really important for digital tuning type of simulations. And of course, there are many more ideas that we're happy to continue discussing with GTT all the time. And with that, I would like to conclude my presentation. Thank you very much for your being here, and sorry, I apologize for going longer than necessary.
No problem. Thank you, Tanai.